Continuing on, talking about stoichiometry, we want to introduce the idea of what's called the limiting reagent. So we'll return to our sandwich example. We have our same recipe for sandwich, same chemical equation for a sandwich. You have 10 slices of bread, 6 pieces of cheese, and 11 pieces of ham. How many sandwiches can you make? Right? We know that this top relationship tells you the necessary ratios. Those ratios are how you make a sandwich. Those ratios do not describe how many of those ingredients you have. You just have some. You bought packages of this stuff at the store. You have some left over. You got 10 pieces of bread, 6 pieces of cheese, 11 pieces of ham. So let's make some sandwiches. When we make sandwiches, we follow this ratio, right? 2 bread, 2 cheese, 3 ham. And that gives us a sandwich. And then those ingredients are gone. Okay, we can keep going. 2 bread, 2 cheese, 3 ham, make a sandwich, they're gone. 2 bread, 2 cheese, 3 ham, make a sandwich, they're gone. We can't make any more sandwiches now. The number of possible sandwiches was limited by how much cheese you started with. You have bread, you still have ham. You could theoretically make more sandwiches if you had more cheese. This always happens when you are making something, right? When you buy hot dogs and hot dog buns, they don't come in packages that are the similar size. One always runs out first because they link together at certain ratios. And if you mix ingredients where they're not at the ratio of the recipe, right? This 2 to 2 to 3, you are guaranteed that one will always run out. And whichever one runs out limits how many you can make. So the cheese is your limiting ingredient here because it has run out. You still have bread and ham left over, but you can't make more sandwiches. Okay, this is a fact of producing things food-wise. It's also true in chemical reactions. So we talked last time that you can use stoichiometry to figure out the perfect stoichiometric ratio of ingredients, of your reactants. I have this much hydrogen. What's the perfect amount of oxygen I should mix in, right? If I mix these masses, if I mix these moles. In general, when you do a chemical reaction, you just mix your reactants together, right? You don't necessarily measure them out to be perfect. You can try to get close, but you're never going to get perfect down to, say, the molecular level. But you can get close. And so the thing is, you're just going to mix them. So here I've just mixed some hydrogen and some oxygen, and they're going to react based on the reaction at the top. The oxygen is the red molecules. They have the 2 lines between the 2 different spheres, and the white molecules with the single line between the ends are the hydrogen molecules. So when they react, they're going to follow the ratio of the chemical reaction. They're not mixed at that ratio, but that ratio is locked in and never changes. So once those react, we know you're going to take the 2 hydrogens, take the 1 oxygen, and they're going to become exactly 2 waters, right? So we can figure that out, the 2 waters that come from right there. So we can figure out how much product we're going to make. This is going to continue. They're going to keep reacting at the 2 hydrogens and 1 oxygen, mix 2 waters. Keeps going. Keeps going. Eventually, one of them runs out. You need both reactants to make this reaction happen. Just like you can't make sandwiches without cheese, right? You can't have this reaction occur if you don't have both hydrogen and oxygen present at the ratios defined by the balanced chemical equation. So the limiting reagent is the reactant that runs out first. Reagent is just a fancy old-timey word for reactant. So it just means reagent in this context. This is one of the contexts where that word stuck around, but it just means reactant. And limiting means that it limits how much of the reaction can happen. You have enough oxygen, right? You still have 1, 2, 3, 4 oxygens. That reaction could still happen, but you don't have enough of the hydrogen. It ran out. It has limited the reaction. So what is limited at the same time is the total amount of water molecules that can be produced, right? That has been limited. That word limiting really does correspond to the amount of product. It limits the theoretical yield. It limits the possible product that you can make because you've run out of that reactant. You can't make any more product. So whenever you have a mixture of reactants, which is in every single chemical reaction, you need to figure out what the limiting reagent is. That will run out first. Everything else is said to be in excess. So in excess means you have extra of it. So it was oxygen in that past example. It was bread in the sandwich example, bread and ham, right? You have excess, you have more of it left over. That is not getting in the way. The limitation or running out of that resource is not why the reaction has stopped. It's running out instead of that limiting reagent. And so whenever you're dealing with a situation where I have just some reactant mixed together, you need to figure out which one's going to run out first. Participation 615, question 3. What is the limiting reagent in this reactant mixture? My reaction is N2 and 3H2, yields 2NH3. The blue reactants, the blue molecules are N2, and the white molecules are H2. And then I've got a box of N2 and H2, and I want to know what is the limiting reagent. Third question on participation 615, due Monday, June 15th at 11:59 p.m. over on Blackboard. Link to the assignment is right beneath the link to these videos. Again, my reaction is N2, which is the blue molecules, reacts with 3H2, the white molecules to make 2NH3. I've got this reactant mixture here, and I want to know what is the limiting reagent in that mixture. All right, so this idea of limiting reagent, a lot of times the language, especially around it, limiting implies that it's an issue or like a problem we need to avoid, but it's not. Instead, the limiting reagent is just a fact of reaction design. When you mix reactants together to undergo a process, to undergo a change, we just want to think about what is the limiting reagent. And a lot of times we mix our reactants in such a way that we can choose what the limiting reagent is, because you can always put more of the other stuff. So for example, when we burn propane, right? So this reaction, my favorite, C3H8 plus 5O2 gives me 3CO2 and 4H2O. So in order for this reaction to happen, I need to have 1 propane molecule and 5 oxygen molecules. But when I mix it together, what we functionally do is use extra oxygen. All of those are going to react, okay? Then they produce the product based on our expected ideas. And so you still make everything in the same, but importantly, you have oxygen left over. That is what is in excess. You have set up your mixture that the propane is the limiting reagent. Remember, the limiting reagent is what runs out. What that means is you don't have any that's left over unreacted. You paid for that propane. Oxygen is free out of the air. So if you have leftover oxygen, because it's in excess, who cares? If you had leftover propane, that means you spent money on fuel you did not burn. There are unreacted oxygens, those are in excess. We can choose to make our reaction mixture in such a way that we guarantee that whatever we don't care, whichever reactant we don't care about is in excess. The reactant we really want to change, the reactant we paid more money for, we want to design to be the limiting reagent. So, and we can see this in how like flames look. So if you say set up a Bunsen burner, run some flames. If you get an orange flame, that means you have an incomplete burn. That orange flame is indicative of the fact that propane is left over. Incomplete burn means you put in fuel and it did not fully undergo this reaction. You have propane molecules that still exist. You paid for all of those propane molecules, but you didn't get as much energy out of them as you possibly could. So if instead in a Bunsen burner, this bottom part, you can adjust the bottom part and let more air in. So you let more air in, that means more oxygen gets in there. So then there's more oxygen, that becomes in excess. The propane is the limiting reagent, which means the propane all runs out. The propane is completely burnt. You get as much heat as possible out of the fuel that you bought. And so you're burning all of the fuel, you get a hotter flame for the same amount of money. And so that's why we can choose to run this reaction with an excess of oxygen, guaranteeing that propane is my limiting reagent. I get a hotter flame, it's more efficient, and I can get, better bang for my buck, literally, because we're paying for that propane and getting more heat, all the heat potentially out of burning it. You can look at a similar example. Iridium, IR, is an element that on Earth, the only place to find it is in meteorites. So if you want to dig it out of the ground, you have to go to a crater, find the meteorite at the bottom, and you get it out. So it costs $32 a gram, right? Remember, grams are pretty small, so this is expensive stuff. So say you go dig a meteorite out of the ground and you find some iridium. You turn that iridium into this gross compound. So you get this. And so what you then do is the steps, we take that and then process it until eventually you produce iridium-3 chloride. So that's a solid that you use. Iridium is used in like really fancy spark plugs. It doesn't really have a ton of applications, but it has some. And so, but the thing is, this iridium is extremely expensive, right? You had to find a meteorite, dig it out of the ground, process it to get this thing. And so what you do then is if we kind of follow the trail, you do this reaction first. So these iridium atoms become this kind of impure solid that's mixed in with some stuff. Then you take that, it goes into the second reaction, and you get this iridium-3 chloride. Okay, so you're spending a lot of money digging iridium out of the ground. You're going to get a lot of money for selling the iridium atoms. So what you care about the most is ensuring that you don't have any unreacted iridium starting material. Right? So you can choose to set up your reaction such that that is always the limiting reagent. So you can figure out, I figured out my mass, I measure my mass of this compound, right? I calculate a smaller mass, I figure out how many moles I have, and I can determine the stoichiometric ratio and say I need 5 grams of hydrogen, right? I need 5 grams of hydrogen. Well, instead of using only 5, you use like 500. You use a ton more. That guarantees that the iridium compound is the limiting reagent, meaning that none of it will be left over. The limiting reagent runs out. And that is really useful. Your body uses this tool as the same way to guarantee you really get really high % yield on your iridium. You've wasted a bunch of hydrogen, but who cares? Hydrogen is way cheaper than iridium. And plus you have some left over, you can just keep reacting more, right? It doesn't necessarily get thrown away. You do the same thing with the chlorine on the second step. If you needed, say, 10 grams, use 1,000 grams. Just use a ton of this other reactant to ensure that you don't have leftover unreacted iridium in any of your reactants, because that would just be waste. You want to maximize as much of this as possible. You want all of that product, because that's what you sell. Right? And if you have unreacted iridium atoms, those are things you aren't selling, so you're not making money off of them. Okay, yeah, we had a participation question in this video. Couple of videos left. Looking for any more questions across those videos. See you there.